Howdy, everybody. Today, I want to talk about the electrical properties of materials and charges and sort of all of those things that I promised kind of at the beginning in our overview of the course video, but to really dive into some deep detail with some of these pieces. And we'll see what I need to do in terms of editing, filming other pieces, because there's often some simulations and or demonstrations videos that this might really test my editing capabilities, or I might just have this sort of stand alone as a pre-lecture and then have a reason for everybody to come to class and do some of those things live and in person. And eventually I'm sure they'll make their way to YouTube, but we'll see if it happens this semester. Be patient with me. Anyways, let's jump right into it. We're looking at the electrical properties of materials, and I mentioned that there were a couple different classifications of types of materials. But before we talk about those, I want to talk about the different types of charges and what they are. I mentioned them briefly before. We had these charges that we called positive charges, and we have charges that we call negative charges, and we also have charges that we call like neutral charges. They have no charge at all, zero charge. And the fundamental pieces, the smallest building blocks that we're going to really talk about and consider in this class are positive charges being things like protons, for instance. These charges that have a charge of 1.602 times 10 to the negative 19th coulombs. We'll probably talk a little bit why we chose this number / where that came from. It's sort of an experimentally derived figure from other kinds of calculations and other precedents that were set. It's mostly historical, and it's kind of just something that we live with and deal with. It's a measurement issue. And in the same way that we kind of build intuition on this is how big a foot is, or this is how big a meter is, or this is how much a pound weighs, or this is how much a kilogram weighs on Earth at the surface of Earth. Those are sorts of things that we're going to develop some intuition with. And that is going to help us realize that, this is a relatively small amount of charge, a single proton. But then as we start getting into, a typical amount of charge that you could have, depending on what you're talking about, it could be anywhere from like the, say, nanocoulomb range, so like a 10 to the negative ninth, or like a 10 to the negative 6 for a microcoulomb. And a fairly big amount of charge in a lot of cases is even a millicoulomb, and a single coulomb of charge is truly an enormous amount of charge in most cases. So we'll start developing a sense of some of the scale of those pieces. But for negative charges, we have these things that we call electrons that have the same magnitude of charge, but this time it's a negative charge, 1.602 times 10 to the negative 19th coulombs. And if we're talking about like the masses of these things, well, the mass of a proton would be, and this is a number you kind of just memorize if you use it enough times, 1.67 times 10 to the negative 27th kilograms, very tiny. And mass of an electron is, of course, even tinier. These are very, very, very small particles, 9.11 times 10 to the negative 31st kilograms. So just looking at the orders of magnitude, with this prefactor being, this one's close to the top, this one's close to the bottom, it's like a roughly 1,000 off. It's like 3-ish more orders of magnitude of difference between these two particles, where 1,000-ish electrons would be as massive as one proton. And so in many cases, what we're able to see is that the way that these huge objects that are built out of many, 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 many moles of these particles, the net charge that they're often able to accumulate is usually because of the flow of electrons moving around. Because they're so much smaller, they're not really bound to the nuclei of objects. They can kind of sit around the cloud of those nuclei and drift around. And if you're only missing, let's say 1 million electrons, and you have so many, 10 to the 30th electrons in your thing, you don't really notice them in terms of the missing mass. But this missing charge, which again, each missing charge matters a lot more than each missing mass, we start to notice these really strong electric effects as we start sloshing some of these charges around. But that big idea is that other than neutrons, at least in this class that we're going to talk about, you don't really have neutral particles. The only way to get things to be neutral is to have a balanced amount of positives and negatives. And yes, there are other particles that we can talk about from physics. We could talk about like muons and kaons and whatever other kinds of things that do have charge. We're typically not going to think about them until we've already mastered some of those skills along the way for how to do some of that problem solving. Sorry. And we can further look at, the more fundamental pieces like quarks or whatever after we've done a lot of the work that we need to do in this class to start really understanding some of those pieces. So we're painting a relatively simplistic picture of the universe as is, where we've got these positive charges, negative charges, each with this plus or minus one fundamental charge is often what it's called, and it's sometimes just called like E, and sometimes it's called like E plus or E minus. And there's also, of course, things like the anti-particles of these things, which have the opposite charges, unless it's like an application problem or some sort of weird experiment thing that we're looking at. They don't really pop up, so I'm not really going to talk about them too much, but they do exist. The last thing I wanted to highlight is, again, the charge. This is the charge of a proton. This is the charge of an electron. The charge of a neutron is just 0. 0.0 is exactly 0. There's nothing, there's no charge. But the mass of a neutron is actually very, very similar to 3 sig figs. It's exactly the same as the mass of a proton. It's very, very, very nearly close to just this mass plus this mass, because that's very similar to how you make them. The quark structure is a little bit different, and there's also things like binding energy, good old E equals mc squared kinds of things that we'd have to take into account. But for our intents and purposes in this class, this is kind of the structure of the fundamental particles that we're going to talk about. But that being said, we then have these larger particles that we're going to work with. Like if we ever had to deal with, say, an alpha particle. An alpha particle is a fancy word for a helium nucleus. So a helium that had an atomic number of 2 is usually 2 protons, 2 neutrons, and then it has 2 electrons kind of quote unquote in orbit in this cloud around it. The quantum mechanical picture is a little bit messy, so we often think of it from this classical perspective. And this net thing, this atom that we call a helium, is usually neutral. But if we rob it of those electrons, it becomes this particle that's 2 plus of these fundamental charges because it lost 2 of them. They used to be in balance, and now they're not. It could be singly ionized, where it's only 1 plus, and it still has 1 electron kind of circling around here. But if we lost both of them, that's sort of the picture that we would see. And the same kind of thing happens if we have these macroscopic objects that are made out of just a whole bunch of atoms, which are made up of a whole bunch of these positives and negatives in here. So that could be something like, I've got a little, maybe a steel BB ball, and its mass is like, I don't know, 3.5 grams. I'm totally just making this up. And I could put onto it some net amount of charge that's like, I don't know, Q. I'll use capital Q. I tend to like to use capital Q's for like a total amount of charge and little q's for like single charges. Sort of an awkward convention, and we'll each develop our own intuitions, and different problem sets have different conventions. But Q is the letter that we use to denote charge almost always, in the same way that M is almost always the letter. Sometimes it's capital, sometimes it's lowercase, those same kinds of pieces. But if I said that it has, let's say, 2.8 times 10 to the negative 6 coulombs of charge, or because I hate writing this, I would probably just say it has this many microcoulombs, right? This is why we invented those SI prefixes. The 2.8 microcoulombs, well, where did this come from? If it's that much positive charge, it had to be because we took away some number of electrons. And at that point, it's a unit conversion problem. You could say, well, I've got 2.8 microcoulombs, but I need to say that, there are 1.602 times 10 to the negative 19th coulombs per single electron. And now when you cross multiply, as long as you do your, times 10 to the -6 here, if you do the math here where you simplify your orders of magnitude, you look at the prefactors, do that math, the coulombs cancel off. That dimension of charge cancels off in this unit conversion. And again, highlighting this unit conversion idea that we're not changing this number. We're just changing the way a number looks when you do a unit conversion. And so if you have this particular ratio, you end up swapping out, okay, one electron is worth exactly the same thing, at least as far as charge is concerned, this amount here. And so you're able to figure out now the number of electrons when you do this essentially unit conversion. At some level, it's a unit conversion. At some level, it's a comparison or a ratio. That's sort of the difference between these pieces versus like a true unit conversion. If I were saying I'm going from microcoulombs to coulombs, that step that I did here, where I swapped that out from 10 to the, let's start out with the microcoulombs, 2.8 microcoulombs times, I could say I have 10 to the -6 coulombs per 1 microcoulomb. This is a true unit conversion because it has no dimension. You're taking charge divided by charge, and so you're really just multiplying by quote unquote the number 1 with no units, but in such a way that these subunits are going to cancel and you're going to get a new representation of that number. You're changing the way a number looks, but not the way a number is, versus this is a comparison. You're technically doing a comparison between electrons and their associated charge, but it still has that structure of feeling kind of like a unit conversion. Really just an opportunity for me to remind you about how unit conversions work. But that would be how you calculate how many electrons we either had to put on this extra, how many excess electrons if it was a negative amount of charge, or how many electrons we had to take away if it were a positive amount of charge. And we'll start getting a sense for some of the scale of those sorts of pieces there. Just checking my notes here, taking a drink of water. It's a good opportunity to pause, take breaks as needed. Always feel free to do those sorts of things at any time. That's part of the joys of recording videos, is you can do that. But in lectures, keep in mind, you and your instructor need time to rest, think, reflect, look at notes, all those kinds of bits and pieces. Okay, so I've talked about our charges, types of charges, how they come up to these pieces, but now let's compare and contrast two different types of balls. I originally said that this was a steel ball bearing, but what if I had a near identical piece of material that it's a very similar mass, but maybe this one is made of clay, let's say. So I've got similar mass, similar size, but I've got one that's made of steel and I've got one that's made of clay. Similar mass, similar size, not identical because their densities aren't identical, but I'm going to put the same amount of charge on each of them. I'm going to say I've got some electrons that I'm going to take away. I'm going to take away that same amount of electrons, this 2.8 microcoulombs worth of electrons. I'm taking away to leave behind a positive charge in this little region here. So I took away some number of electrons. And I'm going to do the exact same thing over here. I'm going to take away exactly the same amount of charge from this region here, leaving behind some amount of positive charge right there. And comparing and contrasting, what happens then in the moments, not even nanoseconds, like a nanosecond is how long this process really takes when we look at the math and observation and experiment and all those pieces. This one is going to change, and this one is not. Because clay is what we call an insulator. And what that really means to be an electrical insulator is that each little pocket kind of is able to hold on to its charges independently of what's going on around it, unless there's some big thing like this triboelectric charging process, and I'll define that word again in a second, where we charged up these pieces by essentially, I guess I'll explain it now. So a triboelectric charging process, triboelectric is how we typically think of it. If you Google triboelectric series, you'll see sort of a ranking of things, and it's basically a ranking of like how much things want to hold on to their electrons and what's going to become charged positively versus negatively if you kind of just rub them together. So think about like, okay, I'm wearing socks, it's a really dry day, I'm rubbing them on a carpet, and then I'm running around the house shocking my parents or siblings or doorknobs or whatever's around because I'm a menace, and this is what like young children do. They just shock each other with socks and carpet. It's the natural order of things. That's what we mean when we talk about triboelectric charging. It's not just I'm taking my Sith Lightning and zapping some charge on here and here. There had to be like a process of how we did that, and that's typically what we call this triboelectric charging. There's two other types of charging that we'll talk about in the rest of this video as we go. So I've charged up these two balls, and I want to compare what's different between them. This insulator is able to hold on to the charges it has, again, unless there was some sort of triboelectric charging that happened to it, or some other charging mechanism. But now that it's just kind of alone, if I think of it as these isolated cells, so I had sort of this like grid of pieces, the positives and negatives here are balanced. The positives and negatives right here are balanced. The positives and negatives here were balanced, but then I took these negatives away. So only this region right here is imbalanced. And the rest of the insulator is able to hold on to these pieces. Now, if we compare that with the steel that's a conductor of electricity, and we'll see for essentially the same reason that explains what an insulator and conductor are. Typically, electrical insulators and electrical conductors are also like thermal insulators or thermal conductors, those same kinds of materials, things like clay or styrofoam or whatever. These things that are good insulators of electricity are typically also good insulators for heat, for mechanisms that we'll understand soon. So in the steel, the difference in this conductor, the hallmark of a conductor is that charges are able to freely flow. Here in an insulator, they were kind of locally trapped in their different little domains. But in a conductor, they're able to freely flow after being moved. So if we have these like pluses and minuses that are usually hanging out around each other, and I had pluses and minuses and I took one away here, think of it kind of like a little dance floor, and these are little partners. These are going to be able to freely walk around the dance floor versus these are tightly bound to their partner, no partner swapping. Versus here, they're able to redistribute until they reach a new equilibrium. And thinking back from Phys 1 in terms of equilibrium, if we're going to be in a static equilibrium from the forces perspective, what that means is that the sum of forces has to be equal to 0. And we'll later learn, probably in the next video, that the electric force is equal to the charge times the electric field for any given charge. And so they have to, because they can't just get rid of their own charge, this can't ever be the term that's 0. In order to make this whole term equal 0, what happens is that these charges are going to redistribute themselves around the sphere. They're going to push and pull each other around until they reach a new equilibrium state. And that equilibrium state is this condition right here, that the electric field inside and throughout the entire conductor has to be 0. And it turns out that the only way that this is going to happen is for all of the charges to be on the outer surface. We'll explore that idea a lot more, but right now we're kind of going to take it as an observationally verified fact that all of these charges are on the outer surface of the material. So as they redistribute, you kind of get this net smaller positive charge distributed around the outer surface. So there's none like in the middle. So typically we only draw them like this because it's hard to draw in 3D. But if you were drawing kind of in 3D, you'd have some kind of around here, have some on the surface. But there's none like in the middle, in the meat of this cylinder. They're all on the absolute outer surface of the material. That's sort of the big difference between an insulator and a conductor. And please, please, please remember this. I'm going to ask this idea is going to come back up all the time. That when I say, like, what's the hallmark between the biggest difference between a conductor and an insulator? It's this idea that their charges are able to slosh around in a conductor, and in an insulator, they're trapped where we place them. through typically triboelectric charging. And there will also be another equilibrium condition. This equilibrium condition will keep coming back again and again and again, and to plant the seed of the other idea, because the E field, if we are able to add it up along a journey, it has to equal a change in voltage, and for conservation of energy reasons, in the exact same way that if I added up force along a path, the negative of that had to be equal to the change in my potential energy. The negative integral of E dot dl is equal to the change in voltage. And because of this equilibrium condition of the E field being zero, well, if I'm adding up a bunch of zeros, it doesn't matter how many zeros I add up. As long as it's on a finite domain, this will always equal zero as well. So the change in voltage is zero, meaning the entire voltage of a conductor has to be a constant in an equilibrium. So every single chunk of the conductor is at the exact same voltage if it's in an electrostatic equilibrium. That's again going to come back up again and again and again as we go through pretty much every portion of this course. These fundamental properties are really embedded and ever present throughout everything that we're going to be doing. Okay, so the next pieces that I want to chat about are those other methods of charging. We talked about this one, this first way of charging, this triboelectric charging, where you take things and you rub them against each other, and you're able to sort of have them get greedy for charges. Some materials are a little bit greedier for charges than others. Again, there's a triboelectric series that we can Google or we'll use. We'll see this in labs and applications and practice problems. And it's often hard to identify which kind is positive and which kind is negative. It's just that there's an imbalance of charge, and there's additional really proper experimentation that we have to do in order to figure out exactly which one is positive and exactly which one is negative, and how we did that and how we define that historically. There's a lot of interesting science history around some of those pieces that we will probably delve into in our labs and experiments and problem solving, and I'm not going to worry too much about right now. Right now, we're just going to know that there's two types, and experimentally, you often have to do some significant work to actually understand which one is which. But it's pretty easy to tell things like, oh, these two charges, mystery charge 1 and mystery charge 2, these attract. So that means it's either this one's positive and this one's negative, or this one's negative and this one's positive. Or if we see, oh, I've got two mystery charges and these are repelling, they're pushing each other apart, it means they're either both positive or they're both negative. But in order to distinguish between those realities, we have to do some additional legwork that, depending on the problem, we may or may not do. Maybe we're only interested in the magnitude of the charge difference, not the actual charge, whether it were positive or negative. Really depends. So we will burn those bridges when we get to them, as other grad school Jacob liked to say in my cohort, and I like that saying, so I stole it. All right. Our second method of charging is going to be called charging by conduction. So charging by conduction is basically just this idea that because of this property of conductors, that if they have some amount of charge on them and it's able to freely flow until it reaches a new electrostatic equilibrium, if I take two charges, so I've got this one sphere that I put a bunch of charge on by taking away some electrons, keep it positive here, and I have a second sphere that's net neutral. So really, it has a bunch of positives and negatives together. And really, this one also has additional positives and negatives that I just haven't drawn because it'd be too annoying to draw all of them. So that's what we mean when we say something is net neutral. It has just as many positives as it has negatives. It has no excess charge, but it still has, a whole bunch of charges inside of all of the atoms that make it up. But I'm only drawing the excess charges right now. And if I take these two objects and I just bonk them together, I say now kith, and then they bonk together, these charges now see, hey, there's all of this giant area over here, this whole region, this whole volume over here, where there's no excess charge. and because we're a conductor and we're able to freely move if there's a reason to move, we're going to set up an E field in order to shove these charges from this high concentration to the low concentration, essentially. And we'll talk a lot more about the math as we get into like E fields and voltages in future classes. But right now, just this idea of charging by conduction is that these charges are free to move, and they're going to redistribute across both of these spheres. So I'm going to draw tinier pluses, because that same amount of charge had to exist. That's the idea of conservation of charge. We can neither create nor destroy charge. We just took the charge that we had over here. Let's say I had 4Q worth of charge total. I've now separated it into, I've got like 2Q and 2Q. And then since they're in equilibrium, if I take them away, they're now 2Q and 2Q. We essentially were able to, at least if we have identical spheres, if they're not identical, if one's bigger or smaller than the other, if there are other factors we might have to consider, it might not be exactly half and half, but they're going to slosh around until they reach a new electrostatic equilibrium with all of the charges distributed around the surface, typically in some sort of symmetric way, especially in this final configuration as we pull them back apart. And that's what we think of when we think of as charging by conduction. Charging as they conduct through something. Essentially, you have to make the materials touch. You have to have two conductors in contact. They're effectively a single conductor during that contact, and they redistribute around. Then we can pull them apart. That's typically what we mean when we say charging by conduction. The third type is probably the most convoluted type. It's called charging by induction. And it requires an understanding of certainly of charging by conduction, and some of those properties of conductors are going to come up again, though in a slightly different way. And charging by triboelectric charging is typically how a charge imbalance is established in the first place. It's typically the step that is coming before the setup of any of these problems. A lot of times we just say, a sphere has blank charge. It probably got that charge through triboelectric charging in the first place, or through a series of triboelectric charging and then conduction, or triboelectric charging and then induction. This is typically this unspoken seed that helps describe where charge imbalances come from in the first place, but those charge imbalances can then further redistribute through conduction or induction, which I have a particular affinity for. I think it's a really fun and cool process, but it is a sort of multi-step dance. So let's walk through it. In the same kind of way as we had before, I'm going to start with this sphere that has some net positive charge on it. And I'm going to start over here with some other sphere that, again, identical in every way, except it doesn't have that excess charge. Great. The only difference that I'm going to do is that I'm going to do something called grounding this. You know, the sphere, it was bad, it didn't do its homework, it snuck out, whatever. Like, we're going to ground this sphere. And what that means is I'm basically just attaching a metal wire to it, and I'm taking that metal wire and I'm literally just shoving it in the ground or to some other huge reservoir of charge. That's essentially what we mean when we say that something is an electrical ground, that it just has an enormous amount of excess, like, free charges. It's a huge thing. So it's usually electrically neutral or very close to electrically neutral because of how big it is. For instance, the Earth is an absolutely enormous object. It has a ton of mass. And so if we connect to the Earth, we're able to redistribute those charges to this thing. It's basically like, oh, if I pee in the ocean, like, oh, the fishes don't care. Like, there's so much ocean in the ocean. Like, we're not going to notice it. It's a very similar kind of idea. If I just dump, 3 chemical into the ocean, like, the environmentalists can't really care. If everybody starts doing it, obviously becomes a problem. But basically, that's what grounding means. Is it's in some regime where there's such a huge body of charge there. There's so much mass available to it that if we dump excess charge onto it, it doesn't really accumulate a net charge because of how it's able to redistribute that charge. As an example, your car is typically grounded to the frame, And the frame is connected to, all of the other bits and pieces, the big chunks of your engine, the big chunks of your supports and understructure, all the axles, brake, all of those things. And so if you have a small little, zap, aha, I zapped the frame of my car, it doesn't really notice because it's this pretty huge object. That's what a ground really is. So that means that if I take this positive charge and I bring it close, but importantly, I don't touch it, because if I touched it, what we would have is conduction. This positive charge sees this charge over here, which is free to flow, but then there's this huge ground. So basically, a tiny, tiny amount of charge would be left on these, and most of that excess charge would go to the ground if I touched. But we're not going to do that. We're going to bring it very close, but not touch it. And when we bring it very close but not touch it, this positive charge here is attracting negative charges in this thing. So if I draw out a couple of these little dance partners in here, positives and negatives, they're hanging out next to each other. And these negatives are like, hey, there's a big positive guy over here. They're like, and this guy is just doing the like girlfriend meme where he's like looking over at the other one like, how dare you? But these ones, they're moving over here. And so we get this sort of net drift of negative charges closer to the positives, and we're leaving behind the positives over here. So you sort of get this net imbalance, this sort of quote unquote polarization of charges. But these charges have even further to go. We could have taken these ones dance partners, but really we could have taken the dance partners from these ones down here. So in effect, basically what happens is the charges of the same kind get pushed down into the ground, and the charges of the same kind get pulled closer to the surface. So if now, while it's still close, because if I just took this away, nothing would really change. It would all reset. If I just took this away, sorry, I accidentally deleted something. I'm trying to undo that. Guess I'll just redraw it. If I just took this away here, this process would reset, and this thing would just return to normal. Those electrons would run back down to the ground. We would restore this original piece, and we have our net neutral object again. We didn't actually charge anything. And if this is called charging by induction, we have to be able to charge that object. So if we bring this back closer together, and then while it's in this state, we cut this cord. We say, let's take our little eraser and let's go. And so now, if we take this away, these negatives, they want to go. I guess I can just delete it entirely. Thanks. Now, these negatives, they want to go back, but hey, this connection has been severed. They can't through this conductive process. They can only conduct to the edges, and we were able to use this net positive charge to actually induce a charge of the opposite kind through this process of we brought it in close while connected to a ground or some other object. We removed that ground, and then we removed the original charging object that did that charging by induction. And so now we were able to get this piece here. So those are some of the big pieces that I wanted to talk about. I'm going to check my notes real quick, see if there's any other little bits and pieces that I want to talk about. Because I talked briefly about that idea of conservation of charge. We can never create or destroy charge. We can just kind of slosh them around. We learned some of those rules about how and why they slosh around a little bit. It's related to, again, those ideas about conservation of mass, conservation of energy, conservation of momentum. This is a new thing that has to be conserved, and new properties we're getting to be familiar with. I guess the last thing that I might talk about is the structure of molecules, dipoles, kinds of pieces, and how some electric attraction works. So let's say, for instance, I take a styrofoam plate and I rub it on my head and I just slap it on the wall. And people are like, "What? Why would you do that? That's really weird." And I say, because I'm a wacko. I'm crazy. But interestingly enough, when I let go of that styrofoam plate, it just kind of stays on the wall. Now that's kind of interesting. Why doesn't it fall? Because if we look at it from a force diagram perspective, and again, whenever I make a force diagram, I want to make a system schema. So if I have this styrofoam plate, I know that it's interacting gravitationally with the Earth itself. And so if it's interacting gravitationally with the Earth itself, that is going to give rise to a gravitational force pulling it straight down. And so there has to be some sort of net force up. We have to F up somehow if we're going to have this plate not fall. So we have to think, well, okay, that force can't come from nowhere. It has to come from something. But what is it? Because if I said, well, okay, there's an electric interaction, a new kind of force, okay, there'd be an electric force, the plate might have some net charge, and maybe it's interacting with the wall. Okay, if we test that hypothesis, what we're going to find out is that if I charge this plate up, I'll draw a separate picture down here, where I've got some positive charges here. What it's doing is it's pulling negatives closer to it and leaving positives further behind. And it's either able to polarize these or take particles like, for instance, a water molecule that's highly polar, where you've got this hydrogen, this oxygen, and this hydrogen. These are slightly positive and these are slightly negative. So there's this sort of separation of the charges and where they are distributed. And so if these molecules could rotate a little bit, you would also be able to do this. Though the molecule itself might not move, but it might rotate. So there's some amount of polarization, rotation, realignment of charges at some level, depending on what this material is. Even if this material is not a conductor, in fact, it's often better if it's not a conductor, because if it's a conductor, all the charges go in here, fall off to the ground, and then this falls off. So by having at least one or both of these being an insulator, we're able to slightly realign and interact with these charges and get an attractive force. But that only adds complexity to the puzzle, because then, okay, I now have an electric interaction with the wall causing a electric force into the wall, which means now I need to have a force going away from the wall. Crap. But wait, if it's in contact with the wall, this is actually going to be able to explain both of those things, because that contact is going to be both this normal force. It's only about half described by that normal force, which is why I always use a lowercase f to indicate normal force. But then this upward force here is the other part of that, and that's that friction force. Because I have this normal force and I've got some contact with the wall now, I can have friction hold me up. And so the friction and normal force together are able, so I'll write it like this: the friction force plus this normal force together equal the actual force here, this contact force. C for contact, not centrifugal. Centrifugal forces don't exist. Don't write them on your force diagrams. But do write the force that's causing the centripetal effect, or centrifugal feeling, which is, again, something we have to deal with. That's a Phys 1 thing, and I'm certain we will come back to that. Probably when we get to magnetism is when a lot of circular motion pops up in Phys 2. But that, importantly, this is why I really like to have our system schema, because it gives this one-to-one mapping rule for forces. For every one interaction, you have to have exactly one force. And here, that's what we have. We've got this contact force because of this contact interaction on the plate. We've got this electric force because of this electric interaction with the wall. And we've got this one gravitational force here. It's just that this normal force is only a partial description of that contact. The friction was the other part of that that made this a complete description of that force. And it also then helps tie together the way that normal forces and friction forces interact with each other. That's sort of the convention that I like. I had done physics for like 10 or 12 years, something like that, before I came across a system schema, and I was like, wow, I wish I knew about this the whole time. Now, I had good teachers, so I was able to learn all the pieces that I needed. But it's also nice to have a good tool that is really self-consistent. So that's why I did this. I'll probably make another video on system schemas proper and maybe link that here and gesture to this part of the video and you can link there or something. I don't know. I'm still learning out how to do YouTube. I think those are all of the pieces that I really wanted to chat about today with our properties of charges and types of charges, those kinds of pieces. The rest is getting even more nittier grittier into some of these things that I've alluded to. These things like this electric force and that electric field that was paired with it, that voltage, and how do we know how much charge is going to be sloshed between them? Is it exactly half and half? When and why and how much? Those are all questions we're going to be able to get into answering as we delve further and further into this study of electricity and magnetism. So thanks for watching, and I'll see y'all in the next video and or in class if you're in my class. Have a good one.